Okay, so good news. The lectures are now available on our website, bit.ly/minlo24, so you can see all the slides there for yesterday and today, and we'll put material there as we go along. So in this last lecture before our next exercise, I'll talk a little bit about solvers for optimization. This morning we talked about modeling packages. Now we're talking about the other side, the solvers. And I'll split this into solvers for optimization, generic solvers for optimization, and then global solvers for optimization, because they require some additional information. And that's also a preview of some of the material that we cover later in the course. Okay, so we have a mixed integer nonlinear optimization problem. In this case, we have also some integer variables there. And there's a number of information, a bunch of information that you will get if you write your own solver that you can get from the modeling packages. So you get a starting point, an initial guess. You get an indicator or array of what are your integer variables. So when you're modeling it, you don't need to sort the variables into first x and then the y's. They can appear in any order. And the solver will tell, or the package will tell the solver which are the integer variables. They also distinguish structure of the constraint. So it's a little bit of an analysis that goes in where the solver will look, is it a nonlinear constraint? Is it a linear constraint? Is it a network constraint? And it even classifies other constraints. And you can potentially take advantage of that because for certain types of constraints, you can form inverse matrices more easily, for example. And then we talked about this earlier today. You get the package. The modeling language will evaluate functions and gradients. So you get the gradient of your objective function, the Jacobian of your constraints, and you get those in a very efficient way. So doing first derivatives there's almost no overhead compared to evaluating the functions. That's really good. Second derivatives, there's a little bit of an overhead, but it's still very efficient what these packages do. And so you can get the gradient of the Hessian matrix, the Hessian of the Lagrangian. And this involves a Lagrange multiplier, but there's also a multiplier here on the objective function. And the reason is that sometimes you want to not include the Hessian of the objective in your evaluation. So the gradient of the Lagrangian, in this case, there's an additional multiplier, I call it mu. For this problem, that's mu times the Hessian of f, and then plus lambda I, and then the Hessian of the constraints. And so in principle, you can get individual Hessian matrices, but the thing we often do is we sometimes don't want the objective function, in particular when we're looking for feasible points, because then you're just interested in information about the constraints. And the solvers also supply you with the structure of the Jacobian matrix, so the sparsity structure in the Hessian matrix. So that's very good. In return, they also give you nice things like Presolve. So Presolve is operations that are very cheap, that are carried out before you solve the problem. So the problem is often sometimes reformulated. And you can, for example, detect redundant constraints. So this morning we had an example where if a constraint says g of x, gi of x less than or equal to 0, if you can show that the maximum of g of x and y is negative, then you can drop that constraint. Likewise, if you can somehow imply bounds on the variables that fix the variable, then you can also eliminate those variables. And there's potentially a big impact on the solution time when you do this. And the problem that you get is actually a reformulated problem, slightly reformulated problem. All these reformulations are linear operations. So there's no nonlinear, there's very little nonlinear presolve that's being done. And that's very much an open area of research of what could be done in terms of nonlinear presolve. There's been a little bit of work done on quadratic presolve by Nick Gould and Philippe Toin. And then the solver then returns to the modeling package the values of the primal and dual variables, so the optimal values, because that's what you want back, and statistics about the solves. So it tells it about iteration, CPU time, and so on. Okay, so nonlinear optimization problems are very important. So even if we don't have integer variables, or if we relax the integer variables to be continuous, and these instances are always solved iteratively during the tree search. And we'll talk about that later on. A simple heuristic for a non-convex problem, and one that doesn't always work but sometimes might work, is to just try it again. So try a multi-start. A simple heuristic for solving a non-convex problem is to pretend it is convex and just use one of those solvers. They will often work very well for non-convex problems. I have some statistics later. And so just trying these solvers out sometimes works quite well. More sophisticated is you can try some multi-start where you explore the space with different starting guesses. But ultimately, if you really want to solve non-convex problems, you need to solve a non-convex solver. So all our solvers are iterative. They're not as robust as linear optimization solvers. However, they are guaranteed to find the global minimum for convex nonlinear optimization problems. So all the solvers that are out there, they converge to first-order stationary points. And there's a theorem that says for a convex problem, a first-order stationary point is a global minimum. And they often work well for non-convex problems. So on power grid problems, for example, I've experienced that they work really quite well. And those are non-convex problems that we'll see tomorrow. Interior point methods and augmented Lagrangian methods. And they're all a variant of Newton's method. So if you knew Newton's method for solving a linear system of equations, then you can understand what these solvers do internally. It's good to know that they're iterative. We talked this morning that you cannot expect the solvers to satisfy the constraints exactly. They will satisfy the constraints to within some tolerance, usually. And this tolerance is typically 10 to the minus 6 or thereabouts, maybe sometimes 10 to the minus 8 for some of the better solvers. Sorry? The color? The picture? Oh, I'm sorry. Yeah, I put this picture there because it looked pretty, but I can explain the picture to you if you like. Okay, so which symbol? It's trying to illustrate first-order optimality conditions for a nonlinear optimization problem. So we have an objective function, which here is f of x, and those are the contours that I just drew here, these green lines. I don't know if you can see them back there. And there's one constraint, and this constraint is called c of x. So I apologize for that. This is an older picture. And the constraint is this nonlinear curve here. So you want to minimize this function subject to lying on this curve. And you can imagine that there's some kind of hole here, and the function grows out. This is what the contours look like. So if by inspection, this is the solution, right? You're coming downhill up to here, and then you're going back uphill. Okay, so your feasible point. The first order optimality conditions state that I can write the gradient of my objective function, which here in this case I denote as g, so this is not the same g as up there. So g is the gradient of f, as a linear combination of the gradient of my constraints. And so the constraint gradient is just the one that's perpendicular to the constraint. And so this is an illustration of what this optimality condition looks like. And at this point, you're not optimal. It's not a stationary point because the constraint normal is pointing in that direction. So it's sort of perpendicular to the blue line. And the gradient of the objective is pointing upwards. It's very faint, this line, if you can see it. And it's perpendicular to the contour. So we'll come back to this picture. And maybe I'll improve it and make a better job of it. But thank you for asking. So what do you get out of the solver? So ideally, the solver tells you, I found an optimal solution. And that's great. You can celebrate. And if it was a convex problem, you know it's a global solution. If it's a non-convex problem, you might be a little bit unsure. However, the solver could also come back and saying, I couldn't find a feasible point because when I solve this problem up there, I have these nonlinear constraints, and it may not be easy to find a feasible point, a point that satisfies these constraints. And so in that case, what the solvers do is they minimize the violation of the constraint. So the violation of the constraint is this term here. It's the component-wise maximum of Gi, or the components of G and 0. So what does this mean? If there's an I such that Gi of x is positive, then it takes the Gi of x, a positive number. If Gi of x is less than or equal to 0, then this term would be 0. And then you just take a norm such that any norm, for example, the 2 norm or the 1 norm. And most solvers work either with the 2 or the 1 norm. And you then minimize this problem. So what you do effectively is these solvers, if they find that they cannot find feasible constraints, then they tell you that there is that this number here will be positive. So there's some constraint for which Gi of x is positive that you can't satisfy, or maybe more than one constraint. So that means that the problem is infeasible if the constraints are convex. And what you can do in that case is actually just look at the residuals. And the solvers will tell you which of the constraints are infeasible. And that might tell you that you made maybe a mistake when you wrote the model. Okay, this is also a good outcome because we cannot guarantee that the problem is feasible. The problem may not be feasible. It may be overspecified. And so this is also a good outcome for the solvers. These next two outcomes are not very good. So iteration limit. So either it took too much time or it took too many iterations. And that typically indicates either slow convergence or that there's something wrong in your model. So for example, I've seen examples where you have a non-smooth function. So the solvers all assume that you have smooth, twice continuously differentiable functions. If you happen to have a non-smooth constraint that you just put in there, then the solvers don't work very well. And you will usually see what then happens is that you get a feasible point, but you don't satisfy the first order optimality conditions. It could also be that the constraint qualification fails. And I didn't tell you what a constraint qualification is, but somebody asked yesterday, so I put it in there. So that's not a good outcome. What you can do in that case is try a different solver. So different solvers work differently. And the last one also indicates slow convergence. Step got too small. That usually means that there's something going on in the workings inside the solver that it starts to fail to make progress. So some solvers, what they do is they compute a search direction that's downhill, and then they take steps backwards until they can make descent. But if this step backwards, the step that they eventually compute is too small, if it's 10 to the minus 16 or so, then you're not moving anywhere. And so they will print out a warning message and say there's something fishy going on in your problem. And in those two cases, it's really good to look back at the problem and ask yourself, are these functions smooth? So it's not very satisfactory if you come from linear optimization that these solvers are not as robust, but nonlinear optimization is much, much harder. And there are many, many more ways to make solvers look bad than in linear optimization. In mixed integer and nonlinear optimization, it's even harder. So there's basically two outcomes. You either find an optimal solution or you reach a time or iteration limit. And if you find an optimal solution, then if you have a convex mixed integer nonlinear problem, you're in good shape. You have a global solution. Otherwise, you don't know what's happening. Time and iteration limits, it's usually good to look at the log files. So for all the solvers, you can print out statistics as they go along, and you can look at those and sometimes learn if there's something in your model that you should change. So what you should do if your solver fails, well, try a different solver, right? If you go to a friend of yours and ask them what's the constraint qualification and they don't know it, you go and find a different friend to ask. So solvers behave differently for different classes of problems. So here's a little illustration. This is a set of instances. They go from left to right. it's a mixed integer PDE constraint optimization problem, but that's not really important. The discretization increases from left to right. So this is on a 16 by 8 mesh. Over here, it's 256 by 128 mesh. The rows are different solvers. And what we're trying to do is we're trying to recover these red regions here. So the optimal solution looks something like this. And so initially, all the solvers do a reasonably good job. And then some solvers continue to do a good job. This one there, the second one down, Bonmin, branch and bound does a pretty good job. But it fails completely on the largest problem, whereas this next one, Bonmin hybrid, does quite well. So different solvers will give you different results. And they were all run with a 3-hour time limit. So that doesn't indicate that they found the global solution. This is just the best solution that they found. And some of them find really horrible solutions. And if you have, this is just one class of problems. If you have different classes of problems, this becomes even more diverse. So I'll talk a little bit now about global optimization solvers, because that's sort of, you need more information here. And so in this case, it's not sufficient if you write a global optimization solver, you really need to know more about your problem. You need to know about the functional form that's presented to you. And so the global optimization solvers need information such as the computational graph. And so the computational graph up there, I have an expression for a constraint. A and B are just some arbitrary constants. And I have some nonlinear expression there. And the way to interpret this computational graph is that you start off by basically assigning variables to the leaf nodes at the bottom of the graph. And then you write the expressions as intermediate nodes in your graph. So W4 is X4. There's a cosine times of X4. So that becomes a W7. You sort of assign a new variable placeholder for that. W2 times W3. So there's an operation here that multiplies two variables. And there's an operation here that squares the variable. And you keep putting operations together in this computational graph. So this operation here multiplies W6 and W7. So that's this B2, X2, X3 term. And then at the end, it's just a simple addition. So this computational graph is a convenient way for storing information about nonlinear functions. And it's not unique. So I could have written this in a different way. This is not the only way to write the computational graph. It also allows me to easily compute derivatives, because I can use this same computational graph. Moving upwards, I can compute the function value, and then if I reverse it, I can actually compute gradients. So I can sort of go back down and compute gradients, and that's what's done in automatic differentiation. So this is additional information that the modeling language needs to supply to the solver so that they know how to handle these nonlinear functions. And sort of looking forward a little bit, so here's a list of mixed integer nonlinear global optimization solvers. And almost all solvers are based on forming linear relaxations using this computational graph. So you take a simple expression such that up there xk is equal to xi squared, and you replace this. So here's xi, there's xk squared, and you have typically lower and upper bounds, and so you replace this non-convex expression, this line, by, for example, a convexification, which is you take the secant that joins the lower and the upper bound, and you replace it by this whole area here. So that's a convex relaxation. This whole area here is a convex relaxation of this function here. You can see it's a convex set because now any point, if I connect any 2 points, the points along the line still lie inside the set because I've sort of added this volume to it. When you're adding more freedom, more volume to your optimization problem, you typically allow it to find better lower minima. And so that means that the relaxation that I create in this way has an optimal solution which is probably much lower than the true optimum value, because I have the freedom to choose other values for xk given my xi. So I can choose a value in here, for example, which is not a feasible point. You can strengthen these things, and that's part of what we'll talk about later in the course. So for example, if xi turns out to be integer, then you can strengthen this area here to adding additional cuts between the integer points. And so that then becomes a much smaller set potentially, which is nicer because it gives you tighter relaxations. Okay, so, and all these solvers, they all say LPBB, so that means linear programming or linear optimization with branch and bound, except the top one and the one LGO there, that are different techniques. So a question that you could ask is, do we really need global solvers? And I asked myself that question, and I did a little experiment, and I looked at 20 problems that I just took. There were small instances that I could actually run easily. And so if I do something like a branch and reduce, which corresponds as a global optimization solver, then I solve all of these problems and I find the global solution to all of these problems. So this is both for nonlinear optimization and for mixed integer nonlinear optimization. But then for the nonlinear solvers, I sometimes get good answers. So Nitro and IPOpt are two solvers, they're interior point methods. They solve 17 of these problems, which is pretty good. That's a high percentage. And they find the global solution in just over half. And then for the min-low solvers, it's not quite as good. So the solvers there are not doing quite as well. So we need global optimization solvers. That's what this slide is saying. You should stay for the second week. It's not going to be done after week number 1. So even though I tell you that you could initially just try the local solvers and see what happens, it's usually good to have a global optimization solver as well. Right, and so, yes, was there a question? No, there was not. Okay. Right, so really this was just a brief, short introduction into what the solvers do so that you have a little bit of background when you do the exercise this afternoon. You don't need to worry about gradients and Hessians and Lagrangians and all that. That will all magically happen behind the scenes. If you want to write solvers, you have to worry about that and learn how to do that. You also don't have to worry about the computational graph. That's all constructed internally and processed internally and then given to the solvers. And the solvers in turn give you solution information, ideally the optimal solution, but also error codes and solver stats. And global optimization really matters. You saw that on the last slide. You can't just get away with local solutions. That's it. So let's do some AMPL coding, I think, in the afternoon. Or, yep. Unless there are questions, of course. Yeah. No, what we do here is, this is almost another lecture. What we do here is we start off with a nonlinear optimization problem. I'll just put one up here. Let me see, there we go. Let's take this optimization problem at the very top. And so one method is I look at this problem. I'm at a current iterate, xk, that's my current point. And one way to construct my next point is to construct a Taylor approximation of this problem. So I'm going to replace my objective function by a second order Taylor approximation. And so I'm going to do that. So when I write fk, I mean f evaluated at xk. So that's just a constant. I can ignore that. Then I have the next term is the gradient evaluated at xk times x minus xk. And there's possibly a higher order term. So some x minus xk. I'm going to do a second order Taylor expansion, a wk, which I'll tell you in a moment what it is. And I replace my constraints. I use a first order Taylor expansion. So I replace my constraints by gk plus grad gk transposed x minus xk less than or equal to 0. So this, now if you look at this is a linear constraint, a quadratic objective. So this is a quadratic optimization problem. And I can solve this problem. It will give me a new point. This will give me an a putative new point x hat. And with this x hat, I can now either construct a direction d, which is x hat minus xk, and I can now decide how far I want to go in this direction. Pictorially, what you're doing is you have some nonlinear function, and I can only draw it for a for an unconstrained problem, and the minimum to this problem would be here. You might be at a point here. This is your xk there, and you construct a second order model around this point. So you construct some kind of, these are now nice. These are supposed to be ellipses, so they're nice ellipses. And then you move to this point x hat. And you keep doing that. Now, there's a couple of caveats here that make it more challenging, and that is, as long as you're going downhill in the objective, you're doing okay, but you also have these constraints, so you also need to make sure you don't go too far away from the constraints. So there's a whole set of methods that then look at how to balance the objective and the constraints. But the short answer to your question is, what do? We approximate this problem, we form a Taylor approximation, and we compute steps in that for that approximation, and then try to follow those steps to the minimum or to a stationary point. That's the short answer. So we don't have, there's no concept of race in nonlinear optimization, because if you have a nonlinear constraint, so here g of x is less than or equal to 0, it would be very difficult to follow this trajectory, and you might not want to follow it because your objective function might have a minimum there, so you might actually want to go straight to that minimum. So a long answer for a very short question. Nonlinear optimization is a lot harder. We can do another course just on nonlinear optimization, and I can tell you a lot about it, but great question. Okay, let's close and we'll find out where we're going next. Thank you.